Hello, my name is Philipp Sommer.
And my name is Felix Sutton, and we work at the ABB Research Center in Switzerland. Today we will present our paper, VIADUCT, Bridging the Gap Between Testbeds and Real-World Cyber-Physical Systems. The motivation of this work stems from real-world cyber-physical systems, where wireless sensors are used to monitor and control complex physical processes. Examples include monitoring the vibrations of motors and pumps in a ventilation system, monitoring the temperature of high-voltage circuit breaker contacts within a substation, or measuring the flow rate of fluids and controlling valves within a chemical processing plant. So how does a system designer typically go about building such a cyber-physical system? Well, the system designer would typically begin by collecting the execution requirements of the system, such as the expected operational lifetime of the devices in the field, wireless protocol latency, and sensing modalities, and then proceed to design a wireless sensor that satisfies these execution requirements. However, that's not the full story. A real-world cyber-physical system also imposes reactive requirements, which are derived from the underlying physical process being monitored or controlled. For example, such reactive requirements may describe the dynamics of the vibrations observed by a motor and its attached pump, the variation in temperature due to the load of the circuit breaker, or the change in fluid flow when a valve is opened in a complex piping system. We advocate that both execution and reactive requirements are equally important in the design of wireless sensing systems, as these are fundamentally coupled in time. For example, the dynamics of the underlying physical process may force a change in the sensor sampling rate, which in turn may impact the performance of the wireless protocol. So how does the system designer effectively test such a wireless sensing system with respect to both execution and reactive requirements? Clearly, it is not practical to bring the underlying physical process into a laboratory environment. So the state-of-the-art approach is to use a testbed. The wireless sensor network is deployed in a lab, and each wireless sensor is attached to an observer. The observer, hardware and software, monitors the behavior of the device under test. The testbed observer provides some basic triggering through GPIO lines or serial commands, but it does not provide a way to evaluate the reactive requirements, as there is no interaction with the underlying physical process. On the other hand, once we deploy the wireless sensor network into the real world, it only interacts with the underlying physical process through a set of sensors and actuators. As it is not practical to bring the observer infrastructure into the real-world deployment, the system designer is not able to evaluate the reactive requirements and their impact on the execution requirements. In order to address this gap in testing observability, we propose VIADUCT, a testing infrastructure that provides a virtual deployment that seeks the best of both worlds, using the state-of-the-art observer framework and extending it with a virtual physical process. VIADUCT models the underlying physical process and connects it to a set of virtual sensors and actuators. These virtual sensors and actuators provide a functionally correct and time-synchronized interface towards each wireless sensor, thus making it possible to evaluate both execution and reactive requirements of the complete system. In order to describe the structure of a VIADUCT virtual deployment, let's first consider what a real-world deployment looks like. The target device, that is, the wireless sensor under test, connects to hardware-based sensors and actuators, which are then embedded into the underlying physical process. VIADUCT replaces the sensor and actuator hardware with a custom hardware and software component that interacts with a model of the underlying physical process. This virtual physical process consists of two model instances: a local model, which represents the physical process observed by a single target device, for example, the temperature gradient of a specific circuit breaker contact, and a global model instance, which represents the physical properties that are shared between multiple target devices, such as the change in fluid flow throughout multiple sections of a piping network. Philipp will now detail the architecture of VIADUCT, show a demonstration of its key features, and present the results of an experimental evaluation.
In the next few slides, we're going to discuss the implementation of the VIADUCT testbed infrastructure. First, we introduce the hardware and software architecture of the VIADUCT testbed observer. The observer is implemented based on the Xilinx Sync 720 platform. It is a system on chip which combines a processing system part and a programmable logic part. This platform allows us to run software components on a dual-core ARM Cortex-A9 processor as well as implement logic components inside the FPGA fabric and connect them both together. The interface board contains custom circuits used for power profiling the target device, as well as hardware interfaces for serial port logging, GPIO monitoring and actuation, as well as the virtual sensors and actuators. Timing-critical interfaces to the target hardware, such as GPIO monitoring or power profiling, are implemented in the FPGA part of the chip. Each module inside the FPGA is connected to a companion software module running on top of the Linux operating system. All software modules are connected to the message broker for streaming measurement data and to receive commands for orchestration of testbed experiments. Let us now take a closer look at the VIADUCT Testbed controller, which is the central component that takes care of scheduling testbed experiments as well as storing collected measurement data in a database. At the core of our system architecture, we use the open source RabbitMQ project as a message broker. RabbitMQ provides fan-out exchanges for broadcasting messages to all observers, which is used by remote procedure calls to orchestrate several testbed observers during an experiment. In the opposite direction, measurement data such as serial logs, GPIO traces, or power profiling data collected by the observers are forwarded in near real time through the message broker to the database or to stream processing modules. Furthermore, the controller provides a REST API and web interface for users or other systems to interact with the testbed, as well as a Grafana-based dashboard to visualize measurement data. Next, we show how users can interact with the testbed. Performing testbed experiments with VIADUCT is straightforward, as the controller provides a REST API used by scripts, as well as a web interface to submit jobs and to display the test results. To submit the job, the user uploads the binary firmware for the target platform and configures the setting of the experiment. The testbed job will be scheduled and will be executed as soon as the testbed resources are available. After the experiment has been completed, measurement statistics as well as the raw data can be accessed as well. We provide a Grafana dashboard to visualize the power profiling measurements and GPIO traces. A key differentiator of VIADUCT compared to other testbeds is the ability to connect virtual sensor or actuator hardware to the target device under test. So let's have a closer look at how virtual sensors and actuators are implemented by the VIADUCT observer. In this example, we demonstrate the use of the popular I2C bus, but other digital bus interfaces such as SPI or I2S can be implemented as well. A virtual sensor or actuator acts as a slave on the I2C bus, while the target microcontroller takes the role of the master on the bus. Read and write operations from and to the I2C slave are handled by a dedicated softcore processor inside the FPGA fabric. The softcore processor is responsible for emulating the behavior of the actual hardware device. For example, it provides read and write access to the hardware registers where the sensor readings are stored. However, for many application scenarios, it is only necessary to implement a subset of the hardware registers and functionality. The softcore processor communicates with its companion software module written in Python running in the processing system. The software and hardware modules can communicate using a shared memory interface as well as by interrupts through the Linux user space I/O subsystem. Therefore, it is not necessary to create dedicated Linux kernel drivers for each virtual sensor or actuator. In order to interact with the testbed controller, the virtual sensor and actuator software module act as a publisher or subscriber for events dispatched by the message broker. In the remainder of this presentation, we evaluate the proposed testbed architecture using a series of micro-benchmarking experiments. In the first benchmark, we present measurement results for the latency of event dissemination using the message broker architecture. In order to provide a consistent view of the virtual physical environment, changes in the model state need to be propagated as quickly as possible to all observers. For example, let's assume that we have a virtual actuator emulating a light source. When we change, for example, the intensity of this virtual light source, the model of all nearby virtual sensors would also have to be updated accordingly. To do so, the virtual actuator publishes an event to the message broker, which is then broadcasted to all virtual sensor subscribers. We performed a micro-benchmark to measure the latency when delivering an event message from one virtual actuator to two virtual sensors connected to the same testbed backbone infrastructure. In the test case A, the message from the virtual actuator has to pass through the message broker before being forwarded to the two virtual sensors. The mean round-trip time reported is about 5.3 milliseconds in this case. However, certain events have to pass through the testbed controller in order to update the state of the global model. For example, taking into account the state of several virtual actuators at the same time. In this case, denoted as test case B, the controller will then broadcast a new message to all other virtual sensors. We observed that the additional hop through the controller increases the latency to 7.4 milliseconds. We conclude that the VIADUCT infrastructure is capable of updating global model states in less than 10 milliseconds when operating on top of a standard Ethernet backbone. Next, we demonstrate the implementation of a virtual light sensor based on the I2C bus. Our lab setup consists of two VIADUCT observers based on the Digilent RT-Z7 single-board computer hosting the Xilinx Sync system on chip and our custom power profiler and target interface board. The blue board on top of the observer is a Nordic NRF52840 development kit used as the target device. In this experiment, both target microcontrollers run the exact same firmware application. The first observer is using a TSL2561 light sensor to measure the light intensity of a bicolor LED mounted in front of it. The voltage applied to the LED is controlled using a lab signal generator and toggles between two voltage levels, which will change the color of the LED between red and green. The target microcontroller of the second observer is connected to the virtual light sensor implemented by the VIADUCT observer. A software-based model emulates the changing colors by periodically updating the measurement registers of the virtual light sensor. We have further connected a logic analyzer to both targets to inspect the communication on the I2C bus lines. It can be observed that the signal of both targets have the same timing behavior. Furthermore, the application running on the microcontroller generates the same output pattern by toggling a GPIO pin whenever a change in color has been detected. To conclude our presentation, we would like to summarize the two key takeaway messages of our paper. First, we have introduced the VIADUCT Testbed architecture, which abstracts the underlying physical process of a cyber-physical system and thus making it possible to inject stimulus comparable to a real-world deployment. We achieve this by the concept of virtual sensors and virtual actuators, which are linked through a local or global model of the physical process. Second, we have presented the design and implementation of the VIADUCT Testbed architecture, which allows to scale the testbed in terms of the number of observers, as well as allows to extend the testbed with additional services and to interface with external systems, for example, continuous integration servers. Please have a look at our paper for the experimental results from additional case studies not shown in this presentation. We believe that the proposed VIADUCT testbed infrastructure is a step towards more thorough evaluation of the reactive requirements of cyber-physical systems by the means of a virtual deployment early in the development phase. This concludes our presentation, and we will be looking forward to your questions during the Q&A session.